part of our problem now. Let's find the total energy dissipated by the resistor as the capacitor gets to a full charge, and the amount of energy stored on the capacitor when it gets to a full charge. So let's do C next. The energy dissipated by the battery. So let's remember, how do we find the power of a battery, or the power across a resistor? The power across a resistor is current times potential, but potential is I times R. Current times resistance, that's Ohm's law, so it's current squared times the resistance. So we know what the current is. We found that expression a little while ago. Let's just pop that back up. So there's our expression for current. Let's plug in our expression for current. We'll square that and multiply by the resistance. So we've got epsilon over R e to the minus t over tau. That whole guy is squared, and then we multiply by the resistance. So we've got epsilon squared over R e to the minus 2t over tau times the resistance R. Oh, I forgot to square my R down there. Leaves us with a final expression of epsilon squared over R e to the minus 2t over tau. There's the expression for the power dissipated in the resistor over time. Let's find the total energy dissipated by the resistor. We'll do that using a similar process that we did in part B. Let's remember that power is change in energy over change in time. So then du is power times dt. So our total energy is the power over the total time. So that gives us that the energy is the integral of our power, epsilon squared over R e to the minus 2t over tau dt. This integral is not so hard to do. Our limits, since we're going to go for the full energy dissipated by the resistor, we'll go the full range of time, 0 to infinity. So that gives us u is equal to epsilon squared over R integral e to the minus 2t over tau dt, 0 to infinity, equals epsilon squared over R. The integral of e to the minus 2t over tau is minus tau over 2 e to the minus 2t over tau at infinity and 0. Let's see, can we squeeze this in here? So we've got epsilon squared over R minus tau is minus RC, that's divided by 2. And we want to evaluate this at our limits. 1 over e to the 2t over tau. As t goes to infinity, this whole guy goes to 0. Minus 1 over e to the 2 times 0 over tau. This guy is just 1. And that gives us that the energy dissipated by the resistor is epsilon squared over R minus RC over 2 times minus 1. That R cancels, and we have epsilon squared times C over 2. So there's the total energy dissipated in the resistor as the capacitor gets charged up. The next part of the question says, what is the total energy stored in the capacitor? Well, that's something we know from our section on capacitors. Total energy stored in a capacitor is 1/2 times the maximum charge stored squared divided by C. Maximum charge, that's capacitance times potential, and gives us 1/2 times C times epsilon squared. So there's our total energy stored in the capacitor when it has the full charge. Then our last question is an important one to think about. Are the results consistent with conservation of energy? Because one of our assumptions about circuits, one of our base assumptions, is that energy is conserved. So let's see if energy is conserved. So the energy supplied by the battery, we found that in part B. That was equal to epsilon squared over C. And then the energy that gets used up, so we have energy dissipated. And then we also get energy stored. So those are parts C and D. So the energy used up by the battery, dissipated by the battery, is epsilon squared C over 2. And the amount stored on the capacitor is 1/2 C times epsilon squared. Add those guys together, we get epsilon squared C. So yes, energy is conserved.